Okay, so this video is all about the intermediate value theorem, okay? Which basically says that if you have two endpoints that are not equal to each other, then you have a value in between those endpoints. Okay, so let's draw a quick graph and do a little explanation for us before we write it down. Okay, so this is what it says. So we'll deal with the first quadrant here.
If we have the value between two endpoints, then what?
Okay, so first we have some closed interval from A to B. Okay, so we have a closed interval from A to B where both of those things are defined. Okay, so as you would think, we are going to have a y value that goes along with this x value. So this is f of a, right? That goes to this one. And it doesn't have to be there, but just for our purposes, that's where I'm going to put it. And then we have a y value that goes with this b. So we have an f of a and an f of b. Okay, so this is our basic setup to explain our intermediate value theorem. Right, we have a closed interval, so we're dealing with all the points in between a and b. So the first thing about your theorem is your function must be continuous on that interval. Okay, we'll write this down formally. So as long as our function is continuous, right, there's no holes, there's no asymptotes, there's no jump discontinuities, none of that stuff. It has to be continuous in order for the IVT to be valid. Okay, so the IVT says that as long as this is a continuous function, right, so here's some dashed lines, because we really don't know what the function does, but we do know that it is increasing on this interval, right, because our a value is less than your f of b value, so our y values are getting bigger. It could do lots of crazy things, right? It could be cubic, it could go down before it comes up, it could do lots of things. But we know for sure that it does at least this. Okay? So the theorem says that there is a k value in here somewhere, in between your two y values. Okay? Something in between f of a and f of b. That corresponds with some other x value down here. Okay? We're going to label that x value c, right? It really doesn't matter what letter we're using for these things, but just know that there is a y value in between your two endpoints. And this y value will correspond with an x value that is inside of your interval. Okay, so that's what the intermediate value theorem says. That there is some y value between these two endpoints, and that there exists a corresponding x value within this interval. Okay, so let's write that down formally and see what it says. Okay, so first of all, number one, f has to be continuous. No gaps, no asymptotes, no jumps on your closed interval. And number two, your endpoints aren't the same. Okay? F of A, I guess we'll just write not equal to F of B, because it really doesn't matter which one is above the other one. Right? Over here in my example, the F of A could have been up here and F of B down there. Right? It could have been a decreasing function. Right? So as long as they're not the same, then that's the key here for your conclusion. So the conclusion is that there is a k value in between your two given y values. Okay, so there is a k in between here because it's intermediate, right? This is the intermediate value that we're talking about. There's a k value here such that let's see. No, that's not what we want to write. Let's see, that means that there exists a C value. So there's a C, right, on your closed interval such that, this is poor planning on my part, f of c equals k. Okay, so that's how we're going to see it written. So the y value for this given x value is the same as the one that we're looking for over here. Okay, so number one, our function must be continuous on the closed interval, and our endpoints can't be the same. Okay, so then there's a y value in between your two endpoints that corresponds to an x, right? This is an x value in between your closed interval, such that the y value is equal to there. Okay, yes, that's very long worded and probably poorly written, but let's see what it means actually in practice, because that's really what we care about. Okay, so here we have a graph, a piecewise graph, by the way, nice and piecewise. And it says, is there a value for c on the closed interval from -5 to 2? Okay, so highlights, we're looking from -5 to +2. Is there a value of c such that f of c equals 2? So let's draw in our horizontal line. Where is 2? 2 is right here. Does this horizontal line cross our graph anywhere? Yes, it does, right here. Okay, and we're going to approximate that as what? X equals -4.5-ish. Right, if we want to approximate it, since we don't really know, it's right there. So that's our c value. Yes, there is a c value. There is an x value here in between -5 and +2, right? -4.5 is between -5 and +2, where we have a y value of 2. That is true. Our graph does have a y value of 2 between -5 and +2. So does the IVT guarantee that there's going to be a value, right? So now we're talking about guaranteeing. So what is the first condition for our intermediate value theorem? Continuous, right? Is this graph continuous between -5 and +2? Is it? No, there's not. There's a place right here, if I'm graphing this, I make my pencil go to here, and then I have to pick up my pencil and bring it all the way down to here. Okay, so there is a gap, right? This is a jump discontinuity right there. The limit, well, we can say that, let's see, what graph is this? F. F is not continuous on -5 to 2. Right? Because the limits at what value? The limit as x approaches -2, right? -2 is where we have that jump discontinuity. So the limit as x approaches -2 does not exist, right? We have to have a limit everywhere on our continuous interval. Okay, so here we have a spot where, yes, there is an x value, right? It's called -4.5 from your graph where the y value is +2. Okay, but if we didn't have our graph, right, we could say that it's not continuous there, so the intermediate value theorem does not guarantee. And this is what the IVT is going to say. Does it guarantee that you have to have a c value? Right? So number one, it has to be continuous. If the function is not continuous on that interval, then a value is not guaranteed. It could be there, but it's not guaranteed. Okay, that's one of the stipulations of the IVT, is this word guarantee, which is a loaded word. Okay, so how about here? From -1 to 5, now we're changing our interval. Now we're going from -1 to 5. Okay? Is our, let's see, what's the question say? Let's answer the question. is there a value on negative 1 to 5 such that f of c equals 2? Right? Does the line y equal 2 cross our graph anywhere? No, it does not. Okay, so there's not a value of c such that f of c equals 2. That graph does not cross positive 2 in our interval from negative 1 to positive 5. Okay? Does the IVT guarantee a value? Right? So number 1, is it continuous? Is it?
No.
F is continuous on negative 1 to 5. It 100% is continuous on negative 1 to 5. Does this line that I'm tracing right now have any gaps or jumps or asymptotes? No, it does not. That function is 100% continuous from negative 1 to positive 5, right? We have a line. Lines are always continuous at all places, except for in this case at negative 2, because it's a piecewise function. So yes, our function is continuous. Okay? That has been met. But now let's look at your y values. What is your y value at negative 1? Right? Because we have to have endpoints. So the y value at negative 1 is negative a half or so. Right? Here, what's the y value at negative 1? Negative 1/2. What's the y value at negative 5? Way over here. What's our y value over there? Negative 3.5. That's a hideous looking 5. Okay? So yes, with the first condition of the IVT is met, our function is continuous from negative 1 to positive 5. And look at our endpoints. One of our endpoints is at negative 1/2, and the other endpoint is at negative 3.5. Are those endpoints equal? No, right? So those are 2 out of the 3 things that have been met. So the third thing is we have a k value of 2. Is 2 between negative 0.5 and negative 3.5? Right? No, it is not. 2 is not between those 2 numbers. So the IVT cannot guarantee that value because it's not between your 2 endpoints. It can guarantee anything between 0.5 and negative 3.5. Right? So those are the y values that the IVT will guarantee to be there. All the other ones, not guaranteed. Right? So it's about the guarantee. That's why we say no, because the k value that we're talking about is not in between your 2 endpoints. Okay? So there's a couple things we have to check. Number 1, is it continuous? Number 2, what are the endpoints? And number 3, is our value between there? So let's see. What 2 conditions must be true to verify the applicability? Number 1, your function must be continuous. Continuous on your closed interval. Okay? That has to be first. If it's not continuous, then we can have gaps and all kinds of other things. The IVT does not guarantee a y value. And number 2, your given y value that we're looking for, known as k, must be between your 2 endpoints. Okay? If your y value that you're looking for is not between your 2 endpoints, then there's no guarantee that they're going to have an x value that corresponds with it. Okay? It might still, but it's not guaranteed. Okay? So it's the guarantee part that we're looking for. Okay, let's try this with some more problems, some more math problems, and see how you're going to be tested on this. Determine if the IVT is applicable or not, and state why or why not. If it is applicable, find the value of c. Okay, so here we have our nice equation for number 1. Okay, what type of an equation is example number 1? With x on top and x on bottom. This is a rational equation. Okay? With a rational equation, we have to have some restrictions. So what number must we restrict on this rational equation? X cannot be -2, because if x is -2, then we have a 0 in the denominator and our function is undefined. Okay, so that means that we have a vertical asymptote at -2. Okay, just so we know, right? Rationals are not always continuous on the entire interval. But what interval are we looking for? -1 to 3. So is our function, is our rational continuous between -1 and +3? Yes, it is, right? The only place that is not continuous is at -2, because that's where our asymptote is. So number one, f is continuous on -1 to 3. Right? Because the only place that is discontinuous, the only place that has an asymptote, is at -2. And -2 is not in our interval. Right? -2 is not between there. So we're good on the continuity part. Okay, step number 2. We need to find our endpoints. So what is the function evaluated at -1? Okay, what is our y value when x is -1, right? The left endpoint. So we do that by plugging -1 into your equation. So -1 minus 3 over -1 plus 2. That's -4 over +1, which is -4. So when x equals -1, our y value is down here at -4. Okay, there's our first endpoint. Right? In this case, your left endpoint, because -1 is the left side of your interval. And now we check for the right endpoint. So we plug in 3. Okay, so f of 3. So we go back in, we have 3 minus 3 over 3 plus 2 is 0 over 5, which is 0. So at 3, we are at 0. There we go. Okay, so those are our two endpoints. Those are your endpoints. So the question is our k value of 2/3, is that between 0 and -4? Is positive 2/3 between 0 and -4? No, right? This is not true. Positive 2/3 is up here somewhere on your graph, right? Maybe that's positive 2/3. Okay, so does the IVT guarantee that there's going to be a C value? No, right? Because our K that we're looking for, our 2/3, is not in between 0 and -4. The intermediate value theorem only guarantees the points between -4 and 0. And 2/3 is not between -4 and 0. Okay, so there is no guarantee there's going to be a C value, right? So it says determine if the IVT is applicable or not, so not applicable in this situation. Why is it not applicable? Because our 2/3 is not in our interval of -4 to 0. I guess it should have gone this way, huh? -4 is the smallest. It still doesn't work either way. Okay? So those are the things that we have to do in every single IVT problem. We have to talk about its continuity, and then we have to find the two endpoints of our function. Okay? So how about the next one? This one says from -4 to +1. Same function, -4 to +1. Okay, so what's the problem with -4 to +1? F is not continuous, right? It's the same graph we had a second ago. and continuous, O-U-S. At what x value? Where is our rational function have an asymptote? At -2, right? Because the graph, I guess let's not talk about the graph. We don't have a graph. Because what does not exist at -2? The limit. The limit does not exist at -2. Okay, and if the limit doesn't exist somewhere, that means your function is not continuous. Okay, like we had a second ago, at -2 we have an asymptote, and it went up on the left side and down on the right. Right, so at -2, the limit does not exist. The left side is going up to infinity, the right side is going down to -infinity. Right, those are not the same places. Okay, so on this interval, from -4 to 1, our function is not continuous. Okay, not continuous. So the IVT does not guarantee there's going to be a C value. Okay, so first we check for continuity, and then we check for Y valueness. All right, let's see about our next one. Okay, there's a lot to this one. So number one, yes, we have a continuous function times a continuous function, so P is continuous. Okay, then we find our endpoints at -2 and at +1, and we compare our value of 5. So yes, 5 is in between there, which means the IVT does guarantee that there's a number between -2 and 1 where that Y value comes out to be 5. Okay, so that's how we're going to use the intermediate value theorem to prove that the existence of a number. Okay, prove the existence of a number. There you go.